Good evening, everybody. I feel like a rock star on this stage. So, yes, my name is Johannes Tammekänd, and I'm the CEO of Sidekik. I'm going to share a story of how to make neural networks speak and what are some of the learning points while we have done it. I would like to ask a question. Who is a data scientist in this room? All right. And who works with languages? Oh, that's cool to see. Quite many. And who would like to become a data scientist? That's glad to see as well. So my story starts very similarly. In 2017, my background comes from cybersecurity. I used to work in NATO, and during that time, I was working also in a cybersecurity startup called Payload Security. And in the beginning of 2017, I wrote it down in my dream journal that I want to work in AI. And that opportunity came for me in the middle of 2017, where we used neural networks for detecting malware. And lo and behold, at the end of 2017, we got acquired by CrowdStrike, which is one of the biggest unicorns in Silicon Valley in cybersecurity. For example, they were the ones when Russia hacked DNC during USA elections, they were the ones who investigated that and found out it was Russian. So I got this crazy offer from them, come to Silicon Valley, 5-figure salary, and I was in a very big crossroads. Do cybersecurity and AI, one of the most coolest cybersecurity startups in the world, or start my own sort of venture. And right now, here I'm standing, I took the hard road. And I would like to share some of the things we have learned during that time as a startup, and especially also in AI. Now, it all starts in 2010. There's a man called Adam who gets a phone call, picks up the phone, and that's how basically the conversation goes. Hello. Hi, it's Steve here. What's Steve? Steve Jobs. The guy's like, is it a prank call? No, I'm for real. Could you please come to Cupertino? And so Adam goes to Cupertino, and 2 months later, he sells Siri to Apple. And the reason why Jobs bought Siri was because he understood interfaces better than nobody else. He was the first one to add graphical user interface to mainstream computers, Macintosh, 1984. They were the ones who introduced mouse, click wheel with iPods, touch with iPhone. And Jobs understood that voice is going to become the next interface. And so now becomes the question, what was that Steve Jobs saw that nobody else saw at that time? And our greatest innovation is not a wheel. It's not a steam engine, but it is our voice. And we have to go back a little bit in time to understand what's the reason. You see, 100,000 years ago, where we were exploring the savannas of Africa, we were basically almost like tigers or other sort of Homo erectus, Homo neanderthals. There wasn't anything very special about us. But about 70,000 years ago, our DNA mutated, and we were given, we learned how to cooperate effectively in large groups. And why we did learn that was because of our language. We could describe very detailed the species before us couldn't. For example, we could build tools that nobody else could. And there was no one person, no one Homo sapiens who did it, but there was groups of 150 people who communicated in language, like we do right now as well. And that's something Jobs understood better than nobody else. And he also understood that the current technology we had at the time had a very big problem, meaning it didn't understand our language. It didn't understand the best technology we have. So Jobs had the dream of adding that language to our computers, to our technology, but something happened. 1 year later, Jobs died, unfortunately. And he was about 4 years ahead than everybody else. So Jobs bought Siri in 2010. And the next device that came to market was Amazon Alexa in 2014, November. So, but during that time, somehow Apple or the people in Apple didn't care about Siri and the voice language interface. And Amazon took off. And as today, about every third person in the USA has a smart speaker in their home. Now, to put it into perspective or context, if you compare that to the smartphone growth in USA, in 4 years, there was about 30% market penetration for smartphones. That's the same what we have for smart speakers. So the interface, Jobs would be very happy about it, but he would also be very mad that Apple wasn't the one who did it. So voice is becoming very large. It is already very large in USA, and it is going to affect us even more and more the days ahead, the years ahead. Now the question is, what's so special about voice, or what's the most use cases for smart speakers today? And most of them are simple things. You know, asking what's the weather, what are the news, adding grocery to your grocery shopping list. And there's also one peculiar or very interesting one, which is really chatting with your voice speaker like a friend, having fun with it. And you can understand why is it so important in a few minutes. Now I'd like to jump more into technology, get it near, put our hands in technology, and look what are some of the most advanced conversational systems we have in the world at the moment. Could we roll the audio, please?
See, how may I help you?
Hi, I'd like to reserve a table for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people, when? Today?
Next Wednesday at 6 p.m.
Oh, actually, we reserve for after 5 people. For 4 people, you can come.
How long is the wait usually to be seated?
When, tomorrow or weekday or?
For next Wednesday, the 7th.
Oh, no, it's not too busy. You can come for 4 people, okay?
Oh, I gotcha. Thanks.
Yep. Bye-bye.
Who knows what that was? I would have many of you. That's so it means we are in an AI event. And now basically what we just heard was Google's AI system booking a reservation for us. So the man speaking was an AI system. Now there's the question, how is that possible? It basically sounded just like a human, right? And the first step is really, let's take a question of you heard audio, for example, what time would you like to book at the table? So the restaurant owner asked that. You heard audio. That gets converted to text through automatic speech recognition. And you also have context. For example, what time would you like to book the restaurant? Or, for how many people, or the metadata. And that is the input, So So the red one is first neural network. Now comes all of the data is inputted to a recurrent neural network. And so that's the second neural network. And that basically neural network outputs, for example, for 7 p.m. please. And now we have a third neural network, which converts the text to audio. And let's take a little bit closer look about the architecture. There are two very interesting aspects here. And the first one is really about recurrent neural networks. So that's also something that Google Translate has used for many years, recurrent neural networks. Not anymore though, because they basically upgrade to a new system. But if you have a neural network that outputs, let's say you translate from a Chinese to knowledge is power. So if you want to know what is the last word, the power, it also looks what's before that. So it has like a short memory. The network has a short memory. And if you combine two of those recurrent neural networks, you get a sequence-to-sequence model, meaning the encoded part is basically, I'll bring in an analogy. If somebody asks a very complicated question from you, the first thing you'll do, you'll start thinking about it. Once the thought comes into your mind, you can think of that as an encoder. Okay, and now the decoder is the one that gives the answer, so you speak it out basically. So that's the part in the previous slide. That's probably not an AI. That was the part, the middle part, the recurrent neural networks, put together. I think he didn't get the memo, did he? And now it's the question of how do you get so good human-like voice? And that's something that Google uses a technology called WaveNet. So you all heard about the robot-like voice before that, very, very robot-like. So how that was before made was you take a lot of words, recorded words. Let's say, for example, if you have Google recorded in an audio, you can split it up to Goo, G-O-O, one part, and G-L-E. And you can start stitching together those words. But that sounds very robotic. Now, what Google does instead of that is they take raw waveforms, meaning in 1 second, there's about 16,000 raw waveforms. So in 1 second, when I speak, there's about 16,000 wavelengths in my 1 second's voice. And that's exactly what Google does as well. When they came out with that in 2016, there was a huge problem, meaning to compute all of those 16,000 raw waveforms 1 second, it took about 90 minutes of computing time. So you just couldn't do it live. But they solved it about 1.5 years ago by making it faster 1,000 times. It's one hell of a jump, making something faster 1,000 times. And now, with 1 second, you can compute 20 seconds of audio. So you can do it real time. And that's something that also Google uses if you speak with Google Assistant. Now, who knows what's the world's largest Turing test? Anybody? I'm going to buy you a pear or a lunch if you'll guess it. All right, I'll give you another hint. It's the Microsoft most successful product in the last 5 years by new users. Sorry, that's quite close actually, but not quite. So it's an AR friend in China called Xiao's, who has over 500 million users. And it's the world's most complicated and advanced conversational system. For example, people have spoken with it over 10 minutes and not understood that it's not a person. How many of you have seen a movie called Her? Did you like the ending? So what about, could Her be, could the Her movie scenario be a real life? Exactly. And currently, Microsoft doesn't release official data about it, but it's estimated that about 20 to 30 million people in China lost that AR friend, like Xiao's. Now it's the question, how the hell can a human being love an AR friend? And what brain researchers have found out that when we speak with an AI system or a robot, our brain doesn't tell a difference if it's a human or it's a not human, because evolution didn't see it just coming. So emotions arouse in us, and we eventually fall in love with it. Now, previously I was talking about one specific use cases with smart speakers, you know, having a chit chat, fun talk with your smart speaker. Now, about a month ago, Amazon just published a paper where they explained and described how they are building a very similar system into their Alexa devices. So tens of millions of people very soon, also in the Western world, will have an AR friend. They can talk about general topic, you know, how is your wife doing, you know, express your emotions and so forth. Now, there's something in a description of my talk, which was about something that happened last year in AR and specifically language. And that was sort of described as ImageNet moment of NLP. Now, to understand that, let's take a look how most of the computer vision systems today are trained and how do they work. So most of the time, we train an ImageNet classifier, 10,000 categories, all understood. So from there, we do transfer learning, meaning in that specific case, there is researchers, Intel researchers, who diagnosed human eye diseases, and comparing without doing transfer learning from ImageNet, they got a lot worse results. And to bring in an analogy, what is transfer learning for those who aren't so familiar with it? It's basically, let's say I know English and I want to learn Germany now. So I transfer some of the knowledge I have about language to German language. So I know the concept, what is even a language? I might know some of the words might overlap. So I transfer that knowledge to the new language I'm going to learn. And so that's very similar with transfer learning neural networks as well. Now, what about NLP? Could we do that same thing in NLP? And from 2013, there was a Google published word2vec, which is word embeddings. So, and what word embeddings do is very simple. It's basically you calculate a vector, just a bunch of numbers for a word, and you look what words are similar to another words. So, for example, hamburger and cheeseburger are very, very similar, but the Ferrari is, you know, is different in that word vector, in that space. And for a lot of time, about 5 years, that method was used in NLP as the first layer. So you take that, you have a bunch of words, you calculate word embeddings, and then you input those word embeddings to your neural network. But there's a slight problem with that. And Google has, which specifically is that Google has done great research about how do different layers learn different aspects. And that's an example with ImageNet and computer vision. So if you, if you start learning from the first layer, the network learns general aspects, for example, edges, then goes more into specific textures and patterns, parts, and then finally you have objects. Now, the word embedding only helps with the edges part. So it's a very shallow learning for NLP. So you miss all of the other goodies down there until last year. So that looks like a very complicated picture, but it's actually extremely simple. So part one is you train a language model. Now, what is a language model? Language model predicts next word in a sentence. And if you have ever used a predictive keyboard in your phone, then language model is behind that. Now, second phase, with the example of, let's say you want to classify spam email or non-spam. You take all of your email unlabeled data and you fine-tune that language model with your email data. That's unlabeled data. It's cheap data, right? And then you take labeled data, your spam or non-spam. And before that, you can also freeze your first layers in the language model and train only basically the last layer with your specific classifier, with the spam one. And why does it even matter? What's the big deal here? Bring you another example. If you train a language model on a Wikipedia articles, and you want to do an IMDb classifier, then it takes 100 times less data, labeled data, with the language model compared to with the labeled data. So there's a paper from Ulfit where they trained a language model on Wikipedia text, and they took only 100 examples of IMDb sentiment classifier, 100 samples. And they got as good results when they didn't do no language model and trained the classifier with 10,000 labeled samples. So it's 100 times, you need 100 times less data with a specific scenario. And basically all of today's NLP models with neural networks use some sort of a language model. And most probably the people with in the NLP would have heard about PERT, which came out in November by Google. And 3 weeks ago, Google released another language model, state of the art, called Transformer XL. Both of those are open source in GitHub, and for both the models, trained models are also open source. Now, I would like to share this question, what do we do? How do we use all of that? And what are some of the things that, how we have shot ourselves in the leg and learned some of the things. We at Sidekik are creating AI humans. So you can imagine sitting behind the table and debating about politics with Donald Trump. Or if you'd like to ask, how did the PC revolution start from Steve Jobs? Or you could ask about rockets from Elon Musk, or learn about physics from Einstein. So the people who are inaccessible to most of us become accessible. Their minds become accessible to us. And we are extremely lucky to have also give faces to our AI humans with collaboration with Wolf 3D. Now, what are some of the mistakes we have done since? Oh, by the way, if you want to, roast Donald Trump, then he's also live in Twitter at Trump Sidekik. One of the biggest mistakes, or I'll bring you an analogy before that. When Tesla started, they started with the Roadster. So that was the low volume, high price car. Next step was Model S, still quite high price, but mid volume. And now they're finally at Tesla Model 3, which is mid price, eventually low price, and high volume. Now, what we did was we thought, okay, we're going to be the smart ones. We're going to build a Tesla Roadster, which we did with Donald Trump, based on only neural networks. And we thought, okay, we're going to scale that same technology to every human. So we can create AI humans of every single one of us. Turn out it doesn't work so well because we need a lot of data, tons of data about a human to basically create a digital human, to create the personality of the human. So that was one of our biggest mistakes. Second mistake was we started with the wrong question of our hypothesis initially was, okay, when we're going to create an AI version of you, it has to help you somehow, help you make better decisions, look over your health and so forth. So we started with that question. But the correct question would have been, what's the conversational first? What is if you saw some of the examples with Amazon Alexa, they were very simple scenarios what people could ask with the quite conversational style. So, and now it's easy as that you can just talk with AI humans with some of the world's greatest AI minds, human minds. It's only conversation. Now it's the question you'll be waiting for. How can you make neural networks speak? And I'm gonna bring you some reasons why you shouldn't before. And first question is, why do you wish to make them speak? What's the business case you wanna solve? And as I've just told about our mistake, it has to be conversational first. Or if you just want to hack away for your sort of fun, then it's also a great way to do it. In most cases, and especially when you don't have a lot of data, you can just solve with simple intents. So it's just a simple chatbot with rules. And lastly, I'm going to emphasize it again, you need a lot of data. With the Google example, Google Duplex example, they haven't given official data, but it's estimated they trained the neural network with hundreds of hours of real conversation. A person picks up the phone, books a restaurant, hundreds of hours. So you got to ask, do you have that amount of data? And now, if you do have that specific case, what are some of the, how do you start? If you don't have a lot of clean data, and if you just want to do it for yourself, learn about it more, learn how neural networks can speak about the conversational part, then there are a few data sets, clean data sets, conversational data sets that you can use. Second part is use a framework. If you don't want to know the nitty-gritty details, how a specific thing in a sequential to sequential model works, or in a transformer, and you just want to see results fast, then use a framework first, get it up and running, and then you can, I suggest, then learn more about it, because otherwise the learning curve is really hard. I also brought out three biggest and the best ones. Denser, the Denser is by Google, NLP is from NL Institute, and Parallel AI from Facebook. We also use Densers ourselves. And the specific problem you want to use first is translation problem. With translation, you have, for example, from English to Germany, but you can use the same model from English to English. So you can have, speaking conversational AI. And the third step is train it iteratively, be lean, and also understand your metrics. Is it going better? Some of the few ones we look is PLO and accuracy per sequence. And the still the best metric is human evaluation. Our vision is 7 billion AIs. And in summary, three big things you can take away from today is conversational AIs and conversational interfaces are becoming more and more important, and we are going to use them more and more. They are going to become a part of our lives. AI friends are going to become part of our lives. For some people, AI loves even. The second part is if you want to do it yourself, do it with the 3 steps I just brought up. Get some clean data. You need a lot of data. Secondly, use a framework. And thirdly, look at your metrics. And I think I forgot the third one, but but thank you very much. My name is Johannes Tammekänd, and I'm the CEO of Sidekik. And if you have, I think Turing, do we have time for questions? I think there is a microphone. Trini, yes. Can bring it here for
Do we have a question here?
Yes.
Can you raise your hand? Okay, here.
Just a question. Do you know how Microsoft managed to boost performance of their data processing in so many times? You said it like 1,000 times.
Oh, Google.
Or Google, yeah.
So you mean the WaveNet specific one?
Yeah.
So it's in analogy, what the new model and the new architecture what we used was in some way similar to Kant's. So they had one teacher model that was very slow, that used from the previous one. So it took about that model, it took 90 seconds. And now basically they had a student model which learned the things from the teacher, and it started improving itself much faster. And eventually they got it so fast. But with most of those cases, the performance is going to take a hit. But for Google, their metrics, they had the same as good as the results with the parent one. Let's go ahead.
Thank you for the talk. I have a question. You mentioned that the best test is human. The best verification against that something works is just a human test, if I understood you correctly.
That's right.
Can you elaborate a little bit more? Like, how do you do that? I mean, do you have like somebody who does the same questions all the time, and then you kind of baseline it, or you just, it's a gut feeling? Or how do you do this?
Have you heard about the Amazon MDirk?
Yeah.
So that's how most of the sort of conversational systems today are benchmarked. So you have automatic benchmarks, and then you send the conversations to Amazon MDirk, and there's a human who basically measures, creates on a 1 to 5 scale, you know, how much sense that sentence does it make, and you know, other aspects. So, and you have enough of that, you know, grades, and you benchmark through that. And that's basically the best we have at the moment, the best benchmarks, or the most reliable benchmarks we have at the moment. Extremely inefficient.
In a way, it's like automation, but with humans.
Yeah,
strange matrix approach.